Hello everyone. So, another day, another math problem. So, we start with a triple. 3, 4, 12. And then we're allowed to pick two of these numbers and switch call them A and B, and switch them out for 3/5 of A minus 4/5 of B, and the other one for 4/5 A plus 3/5 of B. And the question is, and you can choose which one you call A and B, of course. And the question is, can we ever reach this state here? Now, this would seem unlikely, and it is impossible, but it's kind of hard to wrap your head around if this would ever work. I would say that this is not really this is not a very intuitive problem or answer to a problem. So yeah, anyway, okay. So as I said, we can never reach that state, and I'm gonna show you why. So okay, when you see these kinds of things, okay, we have 3, 4, and 5. What does that remind you of? It should at least remind you of a Pythagorean triple, namely a triangle with sides 3. Fuck, I drew that badly. Okay, 3, 4, and 5, and it's called a Pythagorean triple because it's, well, 3 integers that create a right side triangle, the lengths of a right side triangle. And that's what we have here, 3, 4, 5s. And as you know from your Pythagorean theorem, this only holds if the squares, the sum of the squares is equal to the square of the hypotenuse. So therefore, what if we just square it? What happens if we just sum up the squares of both of these things? Okay, so I'll just call this thing here C, and this D. Okay, so then we get that C squared plus D squared is equal to, okay, now I'm writing a bit smaller here because I need to fit. Okay, so that should be, okay, I'm just starting out directly. Okay, so we have 9 A squared over 25, and then we should have minus 24 AB over 25 plus, and then 16 B squared over 25. So that was the first square, and then for the second square we get 16A squared over 25 plus 24AB over 25 plus 9B squared over 25. Okay, and then we see, are there anything? Okay, these cancel out, and okay, so we have here, okay, we have 9 plus 16 A squared over 25. Oh damn. And here we also have 16 plus 9 over 25. Damn. And this thing here is equal to A squared plus B squared. So what happened here? We know that after we switch out our numbers, the sum of the squares is always the same. So that, and since, okay, here we're only picking two numbers, but then of course if the sum of the squares of two numbers never change, then obviously the sum of the sum of all the three squares never changes either. So our invariant in this case would therefore be a squared plus b squared plus c squared, if we call this a, b, and c. This is our invariant, because as we shown earlier, this thing never changes. And what is our starting point here? Well, okay, we have 9 plus 16 plus 144. I think that's 13 squared. Yeah, exactly. It's 13 squared. Okay, so yeah, we're starting out at 169, or 13 squared. And what do we want to end up at? We want to end up at 16 plus 36 plus 144, and that should be, well, okay, here we just have, here we have 4 and 12 and a 3 and a 6, so it's obviously not the same, but the actual number should just be well, yeah, it should just be 196, maybe, and that should not be the square of anything, is it? No, it's not. No, it's not. Maybe it's like 14 squared. If it's 14 squared, please tell me so. No, it's not. No, it's not. Okay, so, well, yeah, okay, so, wait, 44, 16, yes, exactly. So, we're starting out at 169, and we know that this thing never changes, and we want to end up here, where we want to end up at a different number, and which is, well, obviously won't happen, because as I said, it never changes, as invariants do. So yeah, that was everything. Proof concluded, and thank you so much for watching. Have a good one. Bye bye.